Hello, this is lesson 12.6, quadric surfaces. So quadric surfaces are the three-dimensional equivalent to quadratic curves in 2 dimensions, also known as conic sections. So just to review conic sections are curves that can be obtained by slicing a cone by a plane. The 3 main kinds are ellipses, parabolas, and hyperbolas, depending on the orientation of the plane with the cone. Here's another view. Of course, if the plane is perfectly perpendicular to the axis of the cone, you get a circle, which is a special case of an ellipse. Another interesting fact about conic sections is that consequence of Newton's law of motion is that any object that moves in space under the effect of gravity alone describes a conic section. For example, in outer space you have different things that move according to circles, ellipses, parabolas, and hyperbolas, and those are the only options. As you know, parabolas have an axis of symmetry called the vertex. Ellipses have 2 axes of symmetry called the principal axes. Hyperbolas also have 2 axes of symmetry, and they have 2 branches as well. So algebraically speaking, quadratic curves, or conic sections, can be described by a polynomial equation of second degree in 2 variables, x and y. So the quadric surfaces that we are going to do today are surfaces that can be described by also a second degree polynomial equation, but in 3 variables, x, y, and z. So that's the definition of a quadric surface. So quadric surface, so the word is quadric, not to be confused with quadratic. So as a surface in 3D, so described by a second degree polynomial equation in 3 variables, x, y, z. So the general form of the equation of a quadric section looks like this: a x squared plus b y squared plus c z squared plus dxy plus eyz plus fxz plus gx plus hy plus iz plus j equals 0. Okay, so it's a long equation and you see everything is organized here. So first of all of these capital letters from A to J are constants, and x, y, z are the variables. So you see how this equation is organized. You have J is the constant term, and then you have these 3 terms would only have power 1, so these are called linear terms. And then you have these 6 terms called the quadratic term, because they all have a power 2, either a pure perfect cube, a perfect square, like x squared, y squared, and z squared, or a mixed quadratic, like xy, yz, or xz. These are called mixed terms. And that's as high as we go. If you use higher power, then you fall outside of quadric surfaces. Okay, so just like in the case of quadratic curves, there are different kinds of quadric surfaces. So this includes several families. So first of all, there's the paraboloids, and I'll show you what that looks like. And then you have the ellipsoids, which includes the spheres, which we have already encountered. And then you have hyperboloids, and there are two subfamilies. There are hyperboloids of one sheet and hyperboloids of two sheets. Then you have another interesting one called a hyperbolic paraboloid. And then you have the cones and the cylinders. And there's three different kinds of cylinders. You can either have a parabolic cylinder, an elliptic cylinder, or a hyperbolic cylinder. And finally, the planes. Okay, so these are the 8 families of quadratic surfaces. The first 5 are the regular quadratic or quadrics. The last 3 are called degenerate. Because when you slice them with planes, those traces are degenerate conics. So in other words, line. Okay, so to have a visual of what these look like, here are a few images. So here you have an elliptic cylinder. So cylinder, as you know, are surfaces that are parallel to an axis. If you take an ellipse, which is a conic section, and extend it parallel to one of the axes, you get an elliptic cylinder. And you can do the same with the other 2 kinds of conics. So parabolas give you a parabolic cylinder, and a hyperbola extended gives you a hyperbolic cylinder. We have already encountered spheres. Spheres are a special case of an ellipsoid, which is a quadric surface, such that when you slice it with mutually perpendicular planes, you always get an ellipse. Here you have a paraboloid. This is a hyperboloid of one sheet. If you imagine a hyperbola spun around one of its axes, you get this kind of surface. And if you spin it around the other axis, you get a hyperboloid of 2 sheets. 2 sheets that do not touch each other, but is still considered a hyperboloid. Here is the hyperbolic paraboloid, which is kind of a cross between a hyperbola and a hyperboloid and a paraboloid. If you slice it in one direction, you get a hyperbolic trace. If you slice it in a perpendicular direction, you get a parabolic trace, as we'll see in a few minutes. Here is a cone. And here you have a plane, which is just a degenerate quadric. So there's many other surfaces that are not quadric surfaces. Here are just a few examples. You have a torus, a Morin surface, a Mobius strip, a bumpy sphere, and thousands of others. These are non-quadric surfaces. For example, a torus is a quartic surface, which means you can describe it using a polynomial equation of 4th degree in 3 variables. Okay, so if we look a little bit closer at the different kinds, so there are some special cases that we've already encountered. So first of all, if all the quadratic terms are 0, this boils down to the equation of a plane. So you see if A, B, C, D, E, and F are equal to 0, this is just a linear equation, which is the equation of a plane. So if one of the variables is missing, or 2 of them, that means the surface is parallel to the axis of that missing variable, as we've seen already from a few chapters ago. This gives you a cylinder. And depending on what kind of quadratic curve you have in the remaining variables, it can either be a parabolic cylinder, an elliptic cylinder, or hyperbolic cylinder. So some of these surfaces are called surfaces of revolution. Surface of revolution is obtained by rotating a curve around an axis. So in Calculus 1, you typically encounter these solids by taking a curve, rotating around one of the coordinate axes, and getting a three-dimensional surface. And then in Calc 1, you practice calculating the volume contained within those curves, for example. So some of these quadrics are surfaces of revolution, some of them are not. So surface of revolution is a special case. So if you do not have any of these special cases, the way you identify which kind of quadric you're dealing with is by looking at the traces. A trace is the intersection of one of these surfaces with a plane. So we're going to focus on traces now. So the trace of a surface is the curve obtained by slicing it with the plane. So you know, for example, that if you take a cone and slice it with a plane, you get the three kind of conic sections. We can do the same with all the other kind of surfaces that are not cones. So the property of quadric surfaces is that if you slice them with a plane, the trace is always a conic section, or a quadratic curve. Okay, so that's the close relationship you have between quadric surfaces and quadratic curves. So we're going to use our knowledge of quadratic curves to help us identify the quadric sections, or the quadric surfaces. Okay, so to do that, we're going to build a table that allows us to identify quadric surfaces based on the traces. Okay, so this table has two columns. On the left, I have the quadric surface, and on the right, the traces on three mutually perpendicular planes. So we're going to take a surface and slice it three ways with three planes that are mutually perpendicular to each other. So if you have an ellipsoid and you slice it this way, the traces, the three traces, are going to be three ellipses. If you have a hyperboloid of one sheet, you get two hyperbolas. And one ellipse. Hyperboloid of two sheets is very similar. You also get two hyperbolas. But because there's a gap between the two sheets, the third trace will not exist because the plane will go right through the middle and not intersect the surface at all. Okay, if you have a paraboloid, the traces are two parabolas in an ellipse. If you have a hyperbolic paraboloid, you also get two parabolas and a hyperbola. So you can also always look at the difference between these two kinds of paraboloids by looking at the orientation of the two parabolas. If it's a regular paraboloid, these two parabolas have the same orientation. If it's a hyperbolic paraboloid, the two parabolas have opposite orientations. So another way to confirm that you identified it correctly. And finally, if you have a cone, you get two pairs of lines and one ellipse. So because you get lines, that's why the cone is considered a degenerate. If you slice a cylinder perpendicular or parallel to its axis, you also get lines. That's why those are also considered degenerate quadric surfaces. Okay, so finally, to identify and sketch a quadric given its equation. So to identify the type of quadric, first of all, you've got the planes. Those are easy to identify because they're degenerate if there's no quadratic terms. Cylinders are also easy to identify because they have a missing variable. So let's look at all the other cases. So we're going to look first at the easiest kind, which are the untranslated and unrotated and centered at the origin. So these kinds of surfaces can be identified because each variable appears only once. Okay, later on we'll also look at the translated. So if you have a translated, then the variables can appear more than once. But you can create perfect squares by completing the square. And then finally, if you have rotated, that's when you have the appearance of the mixed terms. So terms that have xy, yz, or xz. We're going to leave those aside in this course. Those are more difficult to identify, so we're only going to look at translated and untranslated. So if you have an untranslated quadric surface, you can identify it by its traces, and the planes we're going to use are the three mutually perpendicular coordinate planes. So So these are the planes, the xy plane, yz plane, and xz plane. So these have equations x equals 0, y equals 0, z equals 0. So if the quadric is translated, then you can slice the surface with planes that are parallel to the coordinate planes. Depending on how you've completed the square to translate the quadric surface. So we'll see some examples of that in a minute. So, but first let's start with a simple example. Let's look at a quadric surface with this equation right here. X squared plus y squared plus z equals 1. Okay, so this is a quadric surface. Each one of the three variables appears only once, so this is an untranslated, unrotated quadric surface. You can just slice it with the three coordinate planes and see what we get for the three traces. So if you take the xy plane, which is the plane with the equation z equals 0, if you plug z equals 0 into this equation, you get this equation right here. This is the trace, and it's actually just a circle. Which is a special case of an ellipse. So this is the same thing with the yz plane. So whose equation is x equals 0. So plugging that into the equation above here, we get y squared plus z equals 1, which is a parabola. And the same thing with the third axis, the xz plane, which is when y equals 0. You get another parabola. So if you want, you can solve these parabolas for z equals 1 minus y squared, and z equals 1 minus x squared. So you see both parabolas have the same orientation, they open downwards. So the fact that you have two parabolas and an ellipse identifies this as a paraboloid. And the fact that the two parabolas have the same orientation confirms this. So now let's try to sketch this paraboloid. So taking x, y, z, coordinate axes, let's look at the first trace. So it's a circle in the x, y plane of radius 1. So here you have the unit circle. Again, I'm using dotted points for anything that's not in the first octant. On the yz plane, which is the back wall right here, you have a parabola z equals 1 minus y squared. So it's a parabola that opens downward with the z-intercept of 1. And the third trace is in the xz plane. It's the same parabola, just rotated by 90 degrees. Okay, so if you can see this in 3 dimensions, you see it's basically like an inverted surface of revolution. If you take a parabola, invert it, and spin it around, you get this surface, like an inverted base of a wine glass. Okay, let's try another example. Let's look at x squared plus 4y squared plus 4z squared equals 4. Okay, again, so this is a untranslated, unrotated quadric surface. We'll just intersect it with the 3 coordinate planes. So setting z equal to 0, we get x squared plus 4y squared equals 4, which is an ellipse. Setting y equal to 0, we get x squared plus 4z squared equals 4, which is also an ellipse. And setting x equal to 0, we get 4y squared plus 4z squared equals 4, which is also an ellipse. So the fact that we have 3 ellipses identifies this as an ellipsoid. So now if we want to sketch this, we have to transform these equations a little bit. So this first ellipse here, if we rewrite it in canonical form by dividing through by 4, gives you x over 2 squared plus y squared equals 1. The second one is x over 2 squared plus z squared equals 1. And the third one, dividing through by 4, gives you y squared plus z squared equals 1, which is just a unit circle. Okay, so if we try to sketch this, so in the xy plane, this is an ellipse whose principal axes are 2 and 1. So 2 in the x direction and 1 in the y direction. So it's an elongated ellipse. In the xy plane. In the xz plane, which is this left wall right here, it's a similar ellipse. It's actually the exact same ellipse but with different axes. So once again you have 2 is the principal axis in the x direction and 1 in the z direction. And finally in the YZ plane, the back wall right here, this is just a unit circle that goes from 1 to 1. Okay, so if you can see what this looks like, it actually looks like an egg or like a football that is elongated in the x direction. Okay, last example here. X squared minus y squared minus 9z squared plus 6x plus 8 equals 0. Okay, so here you observe that the x variable appears twice, which means we have to complete that square to get only quadratic terms. So you see you can combine the x squared and the 6x to an x plus 3 squared. This gives you x squared plus 6x. It also gives you a plus 9, which we need to balance on the other side of the equation. And this 8, we can move it to the other side as well. So you see we have x plus 3 squared minus y squared minus 9z squared equals 1. So this is a translated quadric, you see, because the x quadratic term can be canceled out by setting x equals -3 instead of x equals 0. So this surface is just translated by 3 units on the negative side of the x-axis. So if you take the plane x equals -3, this cancels out the first term And what remains is the trace minus y squared minus 9z squared equals 1. And if you notice, this equation can never be satisfied, so you have no trace here. So setting y equals 0, x plus 3 squared minus 9z squared equals 1. This is a hyperbola. And setting x equal to 0, I mean z equal to 0, you get another hyperbola. So the fact that you have, for traces, 2 hyperbola and 1 where the plane does not intersect the surface at all identifies this as a hyperboloid of 2 sheets. You can sketch this if you want. But I'm not going to require that you sketch something. This is a little bit more complicated to sketch. Hyperboloids are complicated, especially when they're translated. So in this case, we're just going to be satisfied by identifying the fact that it's a hyperboloid of 2 sheets.